Okay, so let's start with the first lecture. So we will now start with the beginning of the pipeline that I already showed you before. So as promised, here is it again. So what we will see today is how to deal with the very beginning of this pipeline, how to deal with those stupid pixels, at least to make something usable. So we will not really start today the first block of segmentation. We will really see how to clean up the data, what are the basics to denoise, to restore, to change the geometry of an image, to prepare the data to be properly segmented. So this is a whole course about pre-processing. So again, the pipeline as usual. We are going to see that today, but really the beginning of that. And so we will have different parts in this chapter. We will have a very basic introduction, sorry for the basic aspect of this, on what we are talking about and how we model them. And then we'll talk about pre-processing, and in the next course, we will talk about segmentation and some real applications. So today, the basics of the basics. Sorry for that. It will look certainly trivial, but I think already something towards the end of this lecture of today, you will see that we can quickly move from something trivial to something pretty interesting, actually. I hope you will enjoy it. So what are we talking about? We are talking about images. Images are basically stupid pixels, so basically they live in a space, geometric space, of the pixels, and they have values in some space. So they live in R2, for instance, for 2D images, R3 for 3D images, and they take values, each pixel take a value, which can be a binary, a grayscale, or a color value, or even more. So basically, for me, it's a function, a discrete function in our case, because we'll work with discrete images. And so for the classical 2D images, the M is 2, and so I have a simple 2D matrix, and I can look at it like that, but actually I can look at it like that. It's a 2D matrix with values, basically. And the values can be a scalar value, these are the grayscale images, a value for which you have only one value per pixel, like what you get in an MR scanner, what you get in a CT scanner, what you get in an ecography, whatever, with a black and white camera for those who work with, for instance, very fast cameras. It gives, because it's very fast, they use one single CCD, and so basically you have, for instance, monochromatic images with one gray value per pixel. But it can be also more values, so you can have images in different domains. For instance, if you work with monochromatic images, so grayscale images, you have one value per pixel, and when you display it, you have to display it on a screen which has 3 color components, RGB. So the screen that you use, you need to tell the system which color to display for each value of your pixels. So if you have an image like that, you will most of the time display it like this, where the values of the pixels are mapped onto an intensity of gray. But you can very much display it like that for the exact same data. You can decide to display it like that. What does change is just the coding between the scalar value that you have for each pixel and the color that you use to display that scalar value. And this coding is represented by what is called a color lookup table. So basically, this is a simple table where for each of the values that you can get for your pixels, I'm talking about scalar values here, you define what is the color that you have to display. And for a color lookup table, for displaying an image in grayscale, you say, if my value is 0, I will have black, 0, 0, 0 in RGB is the black color. If my value is 255, imagine that you code it on 8 bits, I will have white, 111, this is the white in RGB. And in between, you have increasing levels of gray. And you represent that in a table, and to display that image, you give to the display system the image, the matrix, and the color table to see how to display them. And if you want to represent it like that, you just change the color lookup table, not the matrix itself. And you say, okay, maybe for the 0 value, I would rather have a kind of a light blue, which is this case. And for the very high pixels, I will have something like a red value. And you can play with the color lookup table without changing, and this is just a display of your data. This is for monochromatic images. So remember, when you see an image like that coming from a sensor which has one value per pixel, you can play with the color lookup table. It doesn't change anything about the content. Yeah?
So for grayscale images, don't we just need one column of numbers?
Yeah, but by default, for a display system, you need to set what is the value of RGB. You have to, because otherwise the system doesn't know and put random colors. So you have to tell him. But for gray, you tell the system, use the same amount for the 3 channels. That's how it works, okay? But now if you have camera that acquires a color image, that acquires typically an RGB image, so the amount of red, green, and blue that the sensor will receive. This is very simply done by having 3 sensors for each pixel, each of them with a filter that will only count the amount of energy that they have in the 3 color channels. So for each pixel, you have a 3 CCD, for instance. So 3 sensors with a filter that will just count how much information you have in the 3 color channels. Then what you get is per pixel 3 values. So we have color images where we have RGB here. And so what you natively receive when you capture that image is each pixel with 3 values, RGB. And you can easily go back from RGB to grayscale if you want. And we will most of the time use grayscale in this course because what we want is to analyze the content of an image. And if the content is not coded by the color, you basically don't care about those 3 channels. You go back to a scalar image, which is much simpler to process, doing processing, writing an algorithm to work with on an image which has one value per pixel is much easier than coping with the colors. So it's very easy to convert an RGB image into a scalar image Y, the others being the other chrominance channels, for instance, and to go back to grayscale. But if you need the information of the color, you get it in the 3 channels. Each channel gets a value which tells you how much of that color you need to use to reconstruct the original color of the pixel. Simple, huh? Okay? So now, that is for the basics of the basics. Now, for those of you who are in electrical engineering, we together last year, we had the signal processing course, and I like to show you a little bit of signal processing because this is my background. So I just would like now to remind you some basic notions of signal processing applied to images. And you will see I will do it with my fingers. I will have very little amount of equations. But just to transpose what you know about basic signal processing, and I'm here talking about sampling, Shannon's theorem, how it applies to images. Very briefly, it's really 10 minutes of Shannon on images, so very little. But let's try to remind you that. So what is an image? For me, it's a function. It's a 2D signal. But it's a signal. If it's a signal, I can, and I like that, I can try to calculate its Fourier transform, right? You all know the Fourier transform of a 1D signal. Well, it also exists for 2D signals. And it's pretty much the same. It's just a double integral. But it's pretty much the same. You convert a 2D image, which is that, into another 2D signal, which is the frequency content of my image. What is the frequency of an image? That we have to think a little bit about that. But in terms of math, it's exactly the same. I have 2D spatial coordinates, and I will convert it in 2D frequency, spatial frequencies. Spatial frequencies. Might not be that trivial. But at the end, what you get is from an image, you get the spectrum of the image in 2D. So if your image is that, you get a 2D spectrum. What does it code? It codes the frequency content of your image. It codes whether you have very shaky pixels, so one pixel, black, white, black, 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 white, black, black, or if you have very smooth images, whether you have noise, which is most probably in the high frequencies, whether you have stripes, whether you have something. And it's 2D because it codes the orientation of that. If you have vertical stripes in an image, you will have very high horizontal frequencies. Because if I look horizontally in my image, I will see very high frequency signal. But if I look vertically, I will see a constant spectrum, as constant frequency. So the 2D aspect of the spatial frequencies really codes the orientation of my frequencies, right? So you have a 2D and you read it really orientation-wise. In that image, the object is pretty roundish. So if you look at each of the lines like that, going through the center, you basically see more or less the same type of signal, which has some kind of sharp transition and then pretty smooth data and then some kind of sharp transition. And it's pretty much the same for all the orientations. So it's not a surprise that the spectrum of that image is kind of symmetrical, roundish. And you read it orientation by orientation, and it gives you each time a 1D spectrum. You can calculate a 2D Fourier transform by a separation law. So if you have only a 1D engine in your computer, you can calculate the final Fourier transform by applying 2 times a 1D Fourier transform. But that's just a computational trick. Why do I show you that? Just because first, to understand what is a spatial frequency, what is this fx axis and fy axis, but also because it has a very practical implication in terms of sampling of an image. We are talking about taking a picture of a real scene, so going from an analog world to a digital world, to a sampled world. We take a picture, and even if you have a super fancy, expensive camera, it is a digital image that samples the reality. So we are talking about sampling, and sampling means sampling frequency, it means Shannon's theorem, it might mean aliasing, recouvrement de spectre, and this is the same in images. And we always have to keep in mind that there is nothing different between a 1D and a 2D signal in terms of sampling. You have the same risks. You need to take care of how you sample. You don't care because Nikon or Canon does, but at some point, people have to care about the sampling, or Apple, of course. So sampling is important. And I like to remind you what you have seen in signal processing, but just applying to 2D. What is sampling? Those who had the course with me will see how I explained it last year. Otherwise, I assume that you all had very good teachers in signal processing. What is the sampling? Yes, sure. Where are you from? No. Those who had Martin Vetterli, I have to say that they had very good courses. So if you sample a signal, what do? Mathematically, sampling a signal means multiplying it by a grid of Dirac impulses, right? You all remember that? In 1D, the mathematical formulation of a sampling process is a multiplication by a grid of Dirac, right? Periodic series of Dirac. Everybody is familiar with that? Who is not familiar with that? Not at all? Sampling you have never seen? So maybe it might be good to go to Wikipedia and have a quick look at what sampling is. Otherwise, you might be a little bit lost. It's not that critical. Don't worry. That will not be the foundation of the rest of the course. But it might be good to have a look at what is the sampling theorem and things like that. So I take an analog signal. I multiply it by a grid in 2D, by a train of Dirac pulses. And by doing that, I get my signal. And by doing that, this explains how I have to do it. Because if I take, in 2D in this case, a grid of Dirac impulses and I multiply my analog image by this grid, I can immediately learn what it does in terms of spectrum. Multiplying by a series of Dirac means what in the Fourier domain? Convolution by what? So I have my original spectrum. When I multiply my analog signal by a grid of Dirac, I will do a convolution in the spectrum of the analog signal by, yes, we move that, and it means that we convolve it by the Fourier transform of a grid of Dirac. And what is the Fourier transform of a grid of Diracs? It's a grid of Diracs. You remember that? Okay, so basically when I take my spectrum of my image, that spectrum, assuming that this is the spectrum of the analog image, I have my spectrum of the analog image that I have in front of me here, beautiful image, analog because you are real, and I take a picture of you, so I multiply the beautiful picture I have in front of me, by a grid of Dirac. So your spectrum, the spectrum of your reality, gets convolved by the Fourier transform of the grid, and the Fourier transform of the grid is a grid. So if I had my grid with delta x and delta y as spacing between the grids, I end up with a spatial grid, a frequency grid with spacing 1 over delta x and 1 over delta y in frequencies, or in pulses 2 pi over. And so my original spectrum gets convolved, means repeated at the location of the different impulses in my Fourier transform of the grid. Clear for everybody or almost everybody? Simple, huh? What does it mean? It means that if I do not take care, I might have aliasing, frequency overlap. If I take, obviously, my sampling period too small, well, if I take very small samples, that's okay, because 1 over delta x will get bigger, and I don't risk to have overlap. But if I really very sparsely sample, so I take big distance between two pixels, 1 over will come smaller, and there is a high risk of overlap between the different replicas of the spectrum. And this is really what we see in images. And you know that to do that, to avoid that, you have to filter. Just before showing you that, when you have done that, if you do it properly, and you know the Shannon Theorem, you know how to do it so that there is no overlap, you have to have a frequency, sampling frequency that is high enough, at least twice the highest frequency in your signal. This is Shannon's Theorem. Okay? If you do that, you will not have overlap. And then you will be able to reconstruct your image perfectly. That's an interesting concept. What does it mean, reconstructing perfectly? Mathematically, it's simple. I go quickly because this is your signal processing course. Huh? If you have this sampled spectrum, the spectrum of the sampled image, to reconstruct the analog image, you just have to filter and get the part in the middle. Yeah, that's exactly what you did in 1D. You all agree? That's exactly what you did in 1D, right? Yeah? Tell me yes? Okay, great. So now that's what we do for 2D as well. We reconstruct by multiplying the spectrum by a box that will isolate the middle part of the spectrum, which means in the spatial domain, the correspondent to the temporal domain in 1D, the spatial domain we convolve by the inverse Fourier transform of a rectangular box. And the inverse Fourier transform of a rectangular box is a sink in 2D. A sink in 2D. Sink in 2D. Simple, huh? So that's the math. So what does it really mean? What does it mean reconstructing the analog image? What does it really mean? I mean, I will never reconstruct the reality. I don't create reality. So what can we do with that? Why is it useful? Well, it allows you to get access to the values of your image at a location between your pixels. You get your sampled data. If they have been sampled correctly, you can mathematically calculate the value of the image at any location, even not on the integer values of your pixels. That's what it is. To do that, you say, I want to know the value of my image here somewhere between 2 pixels. Easy. You just interpolate by that kernel. You just convolve by that, so you take this sink in 2D, okay, fine. You put it where you want, and you interpolate. That means that you calculate the convolution, the weighted sum of the existing pixels multiplied by the weight given by the kernel, and you get at the end of the day a value, and the value is the exact value of the original image that the system has never seen, but that has been sampled. The only problem is that is what? With that is what? That's beautiful theory, yeah? Right? Shannon was a fantastic, incredible guy. What is the only problem with practically doing that? What is the only problem with that? Or with that? Computation? Yes, computation. Why? It takes quite a while because this is infinite. So it takes even more than quite a while. And infinity is very long. especially at the end. Keep that in mind. I already said it in French, so those who are at the signal processing course with me know that. I'm sorry. I'm getting old. Anyway, so obviously we don't do interpolation by a sink, by a real sink, because it's infinite support. So obviously when you do image reconstruction like that, if you want to interpolate correctly, you do the best approximation you can of a sink. Because what we are doing here is really interpolation, right? You have your original pixels that are the sampled version of your reality, and doing an image interpolation means that you want to find the value between the pixels, and if you are good, you want to find the good value of those pixels. So in an ideal world, you would find that this interpolation by using that kernel for interpolating. In practice, you do a little bit less. If you are lazy, you do a nearest neighbor or one linear interpolation. You just take the linear combination of the first neighbors. But you have to understand that when you do that, you use the lazy version of the sink, which is the one that you would love to use. So then you choose, it's your problem. If you are lazy, it's your problem. The image that you will get by interpolating, so calculating the values between the pixels, will not be exactly the one from the original analog image. And if you are lazy, you use a linear interpolation, you have something. If you're a bit less lazy, you use more samples. You can use quadratic interpolation, trilinear interpolation, spline interpolation, whatever. And it is your choice. But you have to know that to know that you are doing a choice of not using the sink for very good reasons, is because it's too long, of course. But that's something you have to know. Why do I say that? Well, because we will need that when we will have to process images. Just to show you what is the aliasing first. So aliasing is really this idea that the spectrum get too close to each other, so there is an overlap. And when you display your image, you basically display the central pattern of the spectrum. There is interference of the neighboring replicas in the middle replica. And so basically, that's what you get when you subsample your image. When you take an image and you subsample it brute forcefully, by taking 1 pixel every second pixel, for instance, you basically reduce your sampling frequency. Sampling more coarsely. And so basically, the different replicas get close to each other, and you might have the appearance of frequencies in your image that do not exist in the original image. This is what we see here. This is a very naive way to do it, but if I take this very old image, I like it because it's very oldish, and you just subsample it by taking 1 point every second point. So I divide my sampling frequency by 2 without doing anything else. You have high frequencies here that are really like high frequencies in my spectrum, on this circle, if you wish. And I subsample my image, so those replicas come down to the middle. And there are high values of the spectrum on the periphery of my replicas, so they really create high values of frequencies closer to the low frequencies, right? They interfere. And indeed, you see that in that image, which is downsampled, so bad quality, but you see the appearance of other frequencies. Here you see stripes at another frequency than that didn't exist at all. It's just inventing frequencies because of the aliasing. So what you have to do, you know it, what to do to avoid aliasing? What do you do if you want to avoid aliasing? You use what? Yeah, you need to filter before. I didn't use any filter here. I just subsampled before filtering, without filtering. You need to filter your image. You have to remove the frequencies that will overlap with the baseband when you do it. So basically, you have to clean the shirt. You have to remove the stripes before. So you do a low-pass filter that will make the shirt uniform, and then there will be no frequency appearing there. Of course, there will be no those stripes neither. That's life, okay? But why do I insist on this question of sampling? It's because when we do image processing, and when you want to develop your system yourself, you will sometimes have to change the geometry of the image. Rotate it, translate it, warp it, deform it. And this is, for instance, very typical in medical imaging. In medical imaging, we acquire images of the same patient in two different machines, one MRI and one CT scan. And at some point, you want to overlap them to see the same reality seen from the two different machines. So at some point, you need to take your images and find the right transformation that will align the two images. If they are from the same patient, it's a simple rotation translation. If you want to average data from different patients, it might be more complicated geometries. And what I want to see now is how we do those geometrical transformations. It's not difficult, but there is a little trick. Because what I want to do, and I want to show you that for the translation first. What I want to do is to take my digital image and translate it by a translation vector. And obviously this translation vector, I don't want it to be integer. The point is not to translate by 1, 1. That's too easy. For that one, I have no problem. I take my image and I copy it one pixel forward. I want to do a translation of 1.3 pixels. And to do that, you have to be a bit careful. What I want is I have my image on its original grid. You see it here. And I want to translate it by 1.3 pixels somewhere. So either I take the screen and I move it by 1.3 pixel, which is not a very good idea, or I leave the screen where it is, and I want to calculate what is the picture that I have to display on the grid of the screen, so that I will have the impression that the image has been translated by 1.3. So I'm kind of joking by saying that you don't want to move the screen, but that's really the truth. You don't want to use the translated grid. You want to leave your screen where it is. The pixels remain where they are, but you have to tell the system what is the value that you have to display on those pixels such that the results corresponds to the translation of the original image. Yes? So basically, you have your original image, and you know that in the analog world, this pixel after translation will basically, for instance, arrive here, because in this case, my translation is that vector. So you know that this pixel will come here, but you don't really care, because this pixel doesn't exist on your screen. What exists is the same grid, and you have to tell what is the value that you have to display on each of those pixels such that it looks like a translated image. So that's the only thing I want you to remember. When you do a geometrical transform like that, what you have to know is what is the value of the pixels of the final image. And to know that, there is only one way to do it. You have to wonder what is the value that you have to put there, and you know it because you just do the inverse transformation, which will tell you that this pixel in the original image comes here by minus t, and then it's a simple interpolation problem that we just discussed a few minutes ago. You want to say what is the value of that pixel in the original image, because that's the one that you want to put there. And to find that, it's a question of interpolation. In an ideal world, we would say we put a sink there, and we do the sum of the values of all the pixels of the image by the value of the sink at that place. We do an interpolation, we do a convolution. But it takes time. And so you say, okay, I want to do a lazy version of it. So the value here is the linear combination of those two pixels. Or it's the linear combination of the 9 pixels or 8 pixels that I have around. Or more, or more. You choose your interpolation kernel, depending on the quality of the transformation that you want to have, and the speed that you have, and the processing power that you have. But at the end of the day, you calculate the value of the analog image here, based on the samples that you have in your original image, and you put that value back to the correct place. So that's the only thing that you have to remember. When you do a geometrical transformation, like this one, you have to calculate the inverse transformation and guess or calculate the values of the pixels in the original image corresponding to the inverse transformation of the pixels that you want to calculate. That's easy, huh? Not very complicated. Just remember that. Because what will happen if you don't do that, you will take the first idea that you have, which is I take that pixel and I translate it by 1.3. It will fall somewhere in between 2 pixels. And you say, OK, I assign that value to the nearest real pixel. And what will happen is that you will have an image full of holes, because there will be pixels that will never be assigned any value, because they are never the closest to one of those translated stuff. So never, 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 never do that. Always do, I want to really fill my image, so for each of the pixels of the image I want, I see where they come from. Just simple like that. For translation, it's very simple. For rotation, it's the same. If I have a rotation, I know how to calculate the new coordinate from the original coordinates. So I know that that pixel after that transformation, so if I take UV here, I calculate the transformation, the rotation, for instance, I will get an XY here. You see the rotated grid. But I don't care about the value of my image here. What I care about is what I have to put on the pixels of my screen. I will not rotate my screen. I will leave my screen straight and rotate the image within the screen. So I want to know what is the value that I have to put there. Well, it's easy. You rotate by minus theta. You get the original coordinates somewhere here. You choose your interpolation kernel. Truncated sink, very big if you have time. Splines, linear, quadratic interpolation. You choose, and you will have more or less good approximation of the real rotated image. And you can generalize that. You can say, okay, my coordinates in my original image can be seen as a general transformation, general linear transformation of the coordinates in the final image. And the things that we have seen here can be particular cases of that. So you see, you can easily have a translation rotation, but also a proper zoom of your image by this linear. But it's always the same. You model, you calculate the inverse transformation, always. And if you make this inverse transformation more complicated with more parameters, you can, for instance, say my inverse transformation is a second-order polynomial of the original coordinates. And by playing with the parameters A and B, you can create strange deformations of your image. You can create strange deformation of your image. So always work with the inverse geometrical transformation. You choose if you want a rotation and translation. There are a few parameters. It's the translation and the rotation angle. But you can also define more complex geometrical transformation by playing with the parameters of more complex functions. But they are always the inverse geometrical transformation. Sorry. And they cope with translation, scaling, shearing, banding of your space depending on the quadratic term, linear term, whatever. And you can have as fancy function as you wish that will create fancy deformations tuned by the parameters of that function. Always, it is the inverse transformation. That image is the original, that is the transformed image. Oops. And so what the inverse transformation says is that basically that pixel is mapped here. So basically here, I will have the same value after interpolation, if you wish, of that. But for instance, that pixel is mapped outside the original image, so it's black. Same here. That pixel, by that transformation, is mapped outside the original image. That pixel will remain in the center. And you see, by calculating the inverse transformation and finding a position in the original image, interpolating around and putting it back at the original location, well, you implement this geometrical transformation. And this allows you, for instance, to register images, so to calculate what is the geometrical transformation to superimpose images of different types in medical imaging. You calculate, you optimize a cost function to find the right transformation between one image and the other to finally come with a nice superposition of your images. And this is what we do every day when we do image registration. And you might invent new ways to do that, but all of them rely on the geometrical transformation of an image to another image, and this has to be done properly. Okay? There is one famous example about that, which is you take an image and you rotate it. And you rotate it 36 times by 10 degrees. Okay, so at the end, you should get back to your original image. But each time you do a rotation, what do? You calculate the rotated image by doing the inverse rotation, that's easy, and the interpolation of the pixels. And depending on the interpolation kernel that you will use, you will, each time you do a rotation, you will lose a little bit of information, because if you don't use a sink, a real sink, complete, each time you lose a little bit. And indeed, you never use a sink. So that's a very nice way to compare different ways to interpolate. You do those 36 rotations with just a 2D linear interpolation. At the end of the 36 rotations, you will basically have a white image. If you use a very nice approximation of the sink, like a spline with some kernels, so more than 2 pixels around, you will see that after 36 rotations, you get back something which is very similar to your image. These are demos that you can easily find on internet. And it's very nice, because you really see that by the same technique, just changing the interpolation kernel, it might be more complex or less complex, well, you lose or not information. And you have to realize that you do that when you transform your images. Okay, that's all what I wanted to say about geometrical transformation. I have to speed up a little bit, otherwise I will never finish. I will break in 5 minutes. And I need that. So, in this first lecture, I will switch one topic to the other, from one topic to the other. I want to see building blocks, and they are pretty much unrelated. So first jump now, I finished the question about geometrical transformation. I want to see a very known and very well used tool, which is called histogram equalization. So nothing related to geometry. Forget about that, or not forget, but at least this is done. Now I want to see another type of pre-processing. What is it? This is something you will see very, very often in the image processing software that you are using. If you're using microscopy, you will see histogram equalization all the time. What is it? We take an image. We have an image. We receive an image. And histogram equalization means working with histograms. What is a histogram? It's the counting of how many pixels of a given color you have. So for that image, which is basically a CT image of lungs, you have this histogram. What does it mean? It means that I have very few pixels that are extremely black. I have quite a lot of pixels that are dark, all those. And I have quite a lot of pixels that have high gray value, all those. With also a little peak here, which is probably the very bright pixels that I have here. And here you see 2 peaks in the histogram. It's probably because you have 2 shades of gray within that area. That's what you receive from your machine. The problem is that, indeed, in the lungs, you have air and you have tissue. And they have a density that is very close to each other, so that with the original image, you really don't see the difference between the air and the tissue. You see it barely in the histogram. This is the air, this is the tissue. And obviously, you see that there are quite a lot of tissue pixels in my image, but you don't see them. They have a gray value which is so close to the air that your eye, even if I do that, your eye is not able to see it. Because it's really bad. It's really bad luck. The machine gives you pretty much the same gray value for those 2 types of components that you really want to see. But bad luck, they have the same density, so they have the same gray value. What we want, what we would like to have, is to say, why don't we take this peak and change the value of all those pixels and assign them a value which is somewhere where I have no other information. So I would want to convert that image, to create a new image, where basically this would go there, this would remain maybe somewhere in the middle, this one might go there, and this one might stay there. So at the end, I would like to have a histogram that is much more stretched. A histogram that is more equally distributed. Okay? Ultimately, the best histogram I want is a histogram where the distribution is really, really uniform. It fills all the possible bins, so that I can see the things with the maximum separation between them. If I consider this histogram in a continuous fashion, I would like to ultimately, after equalization, to have a histogram that is flat, that is uniform. In practice, it's a discrete histogram, so I want to really pull the different columns, the different bins, away from each other. So I will show you how we formulate this problem in a continuous domain, if my histogram is continuous, and then when I apply it to this histogram, you will see that it really stretches, it moves the different bins away from each other. Yeah?
Would it be changing
Pardon me?
Would need to be changing also the information of the image?
Yes, it will. Because this processing is not just displaying. We will change the values of the pixels to make them more visible. But it will actually change the information then. We have to be careful of that. Yes, it does change. So let me, it's 10 o'clock. Some of you have to leave, right? We break. See you next week. And I will tell you that after. So for those who will leave, thank you very much. See you next week. See you on the video. Well, see me on the video. For the others, we continue in 10, 15 minutes. Okay, welcome back. Please take one of the many seats that we have now. So let me try to continue and finish. So I will try to go to the end of this lecture now without breaking so that we can finish in due time. It will not be that long, don't worry. So, welcome back. We are continuing what we were discussing about histogram equalization. So, ultimately, we would like to reshape the histogram and therefore reshape the image, change the color of the pixels of the image to have a histogram that is more nicely distributed, more uniformly distributed as compared to this one, which is by bad luck very uncomfortable and very unpractical, because what we are interested in has a gray level that is very close to another one and we cannot distinguish them. So if we formulate this question in a continuous domain, what we would like is to take this histogram and to find a transformation of each of the pixel values. So what is the new gray level that I have to assign to each of the gray levels of my original image, such that the original histogram becomes a histogram that is more uniform, right? That is the continuous vision of it. You might say, yeah, but it doesn't apply to a discrete histogram. We'll see that. But let's see continuously first. Continuously, what I can easily write is that this guy, the sum of the values of my output histogram, is equal to the sum of the values of my input histogram. Why? Why can I have this equality? Can you think about that for a few seconds? Yes, please.
You have the same amount of pixels.
Yes. This sum, or this sum, is the amount of pixels I have in my image, scaled by the dynamic range of my pixels. But if I have an histogram counts how many pixels I have for each gray value. If I sum that for all the gray values, I have the number of pixels of my image. So what I would like is this to be equal to that, and this gray value here, the number of pixels that I will have if I would manage to get a flat histogram is basically the number of pixels of my image divided by the dynamic range of my pixels. If the integral here is the number of pixels, that means that if I know how many gray levels I have, the height would be the number of pixels divided by that width. N square is the number of pixels. I assume that n is the side dimension of my image. So n square is the number of pixels, to give you an idea. You can name it n if you prefer, but anyway, it's the number of pixels. So basically, I'm aiming at finding the transformation that will replace each pixel of a given gray level by another gray level, such that after that the histogram would be much more uniform. And so I want I can write this equality while J is my target histogram value, which is this. And now I just have to play with this equality. I write it down. So this here, if I write it in a continuous way, I make it simple. Everything is continuous. The integral of J here, which is this, is equal to the integral of H. Nothing special. Sum is replaced by integral. I make it simple. And what I'm trying to find is what is the new value that I have to give to each of the pixels of my initial image, such that when I draw the histogram after transforming this, I get a histogram that is flat. So basically, what I want is to find this transformation T, which maps my P so my value in the original image to a value in the output image. And if I play with this equality here, it's pretty easy because P is here and Q is here. So I can easily find, so this integral is this, so I can easily isolate Q here, which will tell me how I have to calculate Q for a given P. So when I have done this equation, which is this one here, in discrete terms, it's simple. You want to transform your image such that the output histogram looks like that. It's easy. You say, okay, all the pixels with gray level 0 should be transformed to what? Should be replaced by which value? Well, you calculate the sum between 0 and 0 of your histogram, so the bin 0, normalized if you wish, but the bin 0 basically will be mapped back to 0. So the first one, you keep it. Then the second one, P equal 1, you calculate the cumulative histogram from 0 to 1, and this is what you put for the value that you get after normalization is the value that you give to the pixels of gray level 1, and so on and so on. What it means is that each time you take all the bins and you pull them down a little bit. That's what you do. And at the end, by doing that, gray level after gray level, you transform your image into another image that has a much better histogram. You transform your image with this histogram by a new image with this histogram. Of course, it's not uniform because you cannot split one bin into two. The height of all those bins here remains. You cannot split, it's just one gray value. But you do the best you can by pulling them so that you have a more balanced histogram. And it might happen that some bins are created by agglomerating all those bins to reach a level that is closer to the histogram uniform value that you want to have. Those that are higher, you cannot split them because you will not split one pixel into two. But those that are smaller, you can agglomerate them to reach an histogram that looks more like a uniform histogram. And with that, you just realize that this peak is now here, and this peak is now here. There is much more gray levels in between, and you see them now. But you have changed your image. If this is a CT image, which is the case, computed tomography, the gray levels here have a physical meaning. They correspond to the density of the tissue. After equalization, it doesn't correspond at all to densities. So it's just a way to visualize things, and you can post-process those images to calculate, I don't know, to segment the branches. But you cannot calculate by this image what was the density of that tissue. That's gone. You changed it. Yeah, you can map it back, but map it back, it might not be feasible. This is probably not an invertible transformation because you agglomerate things. So be careful when you do that. It's for displaying and then processing the images in a simpler way, but not for quantifying, okay? Close the chapter of histogram equalization. Questions on that? It's okay? It's clear? There's a little bit of trick to go from continuous to discrete, but if you think about that by yourself, you will see that it's not a big deal. So I close this chapter. Now I open the last chapter, which, yes, please.
I just have a quick question.
Sure.
That means, though, that the gray lines, they are there after the transformation. It's just that the value of those gray lines does not necessarily, does not imply the value you would have had.
Exact. So those bars were there somewhere. Some of them are created by summing up existing bars there. Because basically you have too many here and too few there, so you have to make space somewhere. But the values here exist, and you will, those values are mapped in the new histogram. But so basically, things that were with a gray level of 128, for instance, are mapped now to something which might be 70, and vice versa. But they are there, they remain. They might be just agglomerated in one bin. The only point is that since you change the gray values of the pixels, the physical meaning of those, if any, doesn't remain. So I want to open the last chapter, which is denoising and improving the quality of the images. And it's it's long. No, it's not a long chapter, but it's a very vast domain. doing denoising of images, removing the noise, is an endless topic. And I will see it in half an hour, okay, or even less. So I will go to the essence of it, of course, to the simpler things. But at the end of the day, what you need to know is that it's always good to prepare your images. And that is a constant in image processing and computer vision. If you have a way to get good images, do it before doing more complicated analysis. If you can use better lighting, use it. If you can use a better camera, use it. And then you get better images. Otherwise, you have to go to pre-processing to clean up your images. Okay. What we are going to do is to try to remove the noise of an image. What is the noise? It's a random signal. If it would not be random, you would know its equation and you subtract and you are done. It's a random signal. I don't know the equation of the noise. I cannot give the value of the noise for every pixel, but I can give statistical properties. I can, for instance, say that the noise is additive. This is a model. Huh? It's not always true. But with your acquisition system, most of the time or often, you say, okay, the model of this acquisition system is I have a real picture somewhere, but it is corrupted by additive noise because of the acquisition process, which might be the noise which is added to the signal because of the electronics, for instance. And so you basically say, I have a model for the noise. Might be additive, might be multiplicative, whatever. And I have some statistics for the noise. I might say that the noise has a distribution of values. It might be a Gaussian noise if it comes from many different aspects that compensate each other, but in some cases you might say I have some specific statistics because of my acquisition process. I will not go into the details of all the possible cases that you have. At this point, I just want to say that I measure a signal, an image, which is the ideal image corrupted by a noise from which I have some statistics. And this amount of noise is very often characterized by the signal-to-noise ratio, which is estimated and gives you a number which gives you the power of the signal divided by the power of the noise. So basically, a high signal-to-noise ratio is a good sign. It's a good image. And so now we are going to try to see if we can denoise images. And the most natural way to do that is to use simple methods. If my model is this, then using statistical operators, I can say, what is the estimate of my image, my output image? Well, basically, it's the estimate of that, which is this. And if I have a model of the noise which is zero mean, then the expected value of that is 0. So at some point, if I manage to have an estimation of the estimate of my image, I will get a good estimate of my ideal image. Now, this is statistics. Now, how do you do that in practice? In practice, how do you estimate the estimate of a random value, the mean of a random value? You have estimators, right? So how do you estimate, I used the wrong term, I'm sorry. How do you estimate the expectation of a random value? Yeah. So translate that into image. What would you do? Yeah. You want to have a very nice image. Take several of them and average them. You calculate an estimation of your image, and you cancel the noise if the noise is zero mean. It looks stupid, because if you take a picture, you don't want to take 10 pictures. It's not that stupid. That's what systems do. You can have very high frame rate that allows you to take several pictures, average them, and get rid of the noise. You do that in some cameras. You do that also for high dynamic range, but that's another story. And you do that, for instance, in an MRI scanner, in a magnetic resonance scanner. In a scanner like that, the image of the brain that you have seen are the average of several images that I acquire to increase the signal and remove the noise. So this is really done. And it's not stupid. It's really a nice way to do it. It might not be practical in photography, in videos, but in other acquisition systems, if you manage to acquire several images, you have an extremely good denoiser. So do not hesitate to do that. If your data are noisy, acquire many of them, assuming that your process is not dynamic, of course. It's stationary. It has to stay the same over time. But if it's the case, do not hesitate. Acquire several images and average them. You will get rid of much of the noise. MRI does that. Otherwise, you have to do some assumptions. You have to go to heuristic filters that will say the noise has some statistical components, some spectral information that I can remove by filtering. And here we come to very practical stuff. The idea behind that is to say the noise has a spectrum, which is probably different from the spectrum of the image. So if I use a filter, I will remove part of the spectrum, and hopefully that will be the part of the spectrum when I have a lot of noise and little information about the image. So think of that. Take a picture. Imagine its spectrum. There is noise on top of the image, so the spectrum has noise on top of the spectrum of the image. Fourier transform is a linear process. So now, what can we say? What is the spectrum of a noise? In very general terms, what do you know about the spectrum of a noise? Have you heard about white noise? What is white noise? Why is it called white? Sorry, who is speaking?
It's around all of the frequency.
Say it again, sorry? Yeah, so a noise is called white because it has a spectrum that looks very much like the spectrum of the white light, which is a uniform spectrum. So a white noise is a noise that has a spectrum which is uniform over a range of frequencies. Low values, low frequencies, and high frequencies. Now let's compare that to the spectrum of a natural image. Take a picture, maybe not of the scene that you have in front of you, but of a natural scene outside. You take a picture of that. What do you expect from the spectrum of this natural scene? Not much, probably, but at least there is more low frequencies than high frequencies. You have lots of very uniform regions, very low frequencies, and sometimes here and there you have high frequencies when you have sharp transitions, right? So compare a spectrum of a natural image which is more or less on the low frequency side, on top of which you have the spectrum of your noise which is uniform. What would be a good way to reduce the amount of noise is to filter the high frequencies because you will remove a component of the noise where you have a lot of energy, the high frequencies, and you might remove a little bit of the image, but hopefully there is not too much high frequencies in your image. So the very naive 101 filter for denoising is to use a low-pass filter. This is the impulse response of a low-pass filter. Are you all convinced that those three are low-pass filters? Is it super clear for all of you that they are low-pass filters? Might be not. What is a low-pass filter? It's a filter that cuts the high frequencies. Let's do a little bit of signal processing again. Look at that. What is it? In 1D, it would be a rectangle. It's a 2D rectangle. What is the spectrum of a rectangle? We already saw it before, the other way around. A sink. A sink looks like that. So it's really a low pass. It lets the low frequency go and cut the high frequencies, right? So this is indeed a low pass filter. And all those guys are kind of variations around the same. This is not a rectangle, it's a triangle. But a triangle is the convolution of a rectangle by a rectangle. So the spectrum is the square of the spectrum of the rectangle. That was very fast. You will listen that back on the video. I can repeat easily. This is a triangle, and the spectrum of a triangle can be easily deduced from the spectrum of a rectangle. It's also a low-pass filter. Again, check that by yourself. And this is another variations of a triangle, or looks a bit like a triangle. All these are low-pass filters, clear low-pass filters. In the spatial domain, you see it also because they average a pixel by its neighbors. And by doing that, you remove transitions. So you can see it in the spatial domain, and you can see it in the spectral domain. Yes?
Isn't it like a blur filter?
It does, it blurs. But blurring means removing the high frequencies. So blurring means applying a low-pass filter. So blurring If you do that, you really blur your image. But that's kind of what we want. Because if you have a lot of noise, this will remove the high frequencies, and so it will remove most of the power of the noise. And hopefully not too much of the images. But it will blur your image, no doubt, because it will remove the high frequencies. But you cross the fingers that you remove more noise than image. That's the idea. It's not a good denoising filter. It's a denoising filter. And you indeed get blurred images, but also denoised images. You have less noise here than here, but they are blurred because you removed part of the power of the noise, the high frequency part of the spectrum of the noise, but you also remove the high frequencies of your image. You have no choice. You removed everything, of course. But that's what you can do. And doing that, when you have a lot of noise on some types of images, is not that a bad idea. And if you know that you don't have frequencies higher than something, just cut there, and you remove already part of the noise. Okay. There are other tricks that you can, I let you read that on the slide. This is not very important. Now, this was linear filtering. You take that, and you apply that to an image, means that you convolve your image by those filters. Convolving is simple. Now you put it there, and you calculate the weighted sum of the neighbors by those weights. This is a convolution. It's a complicated term for something very simple. But still, you want to do something else. Okay, let's see other types of filters. You can do nonlinear techniques. You can do more sophisticated techniques. They are nice because they might do a bit more sophisticated, intelligent processing of the pixels, but of course they are nonlinear, so you cannot implement them as easy as a convolution. But you can imagine more complicated filters, and I have a few of them in the slides. I would like to concentrate on this one, the median filter. The median filter is a filter that I like very much. The median filter is a filter that I like very much. I like it very much. You get the message? I like it very much. So you have to like it also. Okay? 0.5 chance that I will ask you something about that, to be clear. So what is it? It is a nonlinear filter. So it's a bit more complicated than just applying a convolution, just applying a weighted sum of the neighbors of your pixel. It's a bit more complicated, but it has very distinctive advantages. Let's try to see how it works on a 1D profile. Let's say this is a simple binary, a line of a binary image with pixels 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. So a very simple line of a very simple binary image. And I want to show you how we do a median filter on that line in 1D, and then you can do it in 2D. The idea is simple. You say, I want to do a median filter of a certain size. Very much like my kernels for the linear filter, they were size 3 by 3. Here in 1D, say, I want to do a median filter of size 3 pixels. That means that for each pixel that I will consider, I look at the pixel and its two neighbors. In 2D, it would be the pixel and its neighbors around, 8 neighbors. I look at their values, the 3 of them, the 9 of them, or the 8 of them, and I rank them. I sort them from the smallest to the largest. So I create a sorted list of them, and the median of a list is the value in the middle of the list. It's not the mean. I don't calculate the mean of the values, I calculate the median. I sort them, and I take the value that is in the middle of the list. So sorting them, I have, for that pixel, I have 0, 1, 0, 0, 1, 0. I sort them, 0, 0, 1. In the middle is 0. 0, 0, 1, middle is 0. Yeah? Yeah? Okay? So that one, after filtering, will come back to 0. This one, 1, 0, 0. 1, 0, 0, 0, 0, 1, 0. 0. I continue the same. I can tell you it will give you 0. Here, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. This one, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1. Okay? This one, 1, 0, 1, it will give 1. 1, 0, 1, 0, 1, 1, 1. So what does it do? It replaces the value of a pixel by the median of the pixel and its neighbors. That means that it will remove outliers. It will remove all the things that do not stay for a long neighborhood. Just one pixel alone in a very vast region homogeneous will be completely removed by this filter. So one white pixel in the middle of black pixels, the median will be always the value of the black pixels, right? The mean would not be the same. The mean would be something in between. But the median will be the value of the black pixels. And so this is a pixel that is, this is a filter that is extremely performing when you have that type of noise, which is called salt and pepper noise. Very bright, saturated pixels. And this happens all the time with physical acquisition systems. You very often have saturating pixels because they are illuminated by X-rays, because I don't know what. And with that, if you do a median filter, you get that. And compare that to that. There is an obvious difference. Is that with the median filter, you don't lose the edges. You don't lose the contours. They remain sharp. Because of that, you see, a contour is something that is stable, that is coherent, consistent. It is kept. Only the small things disappear, but a very clear transition from one level to the other will remain after filtering. Because you have a very consistent neighborhood here and a very consistent neighborhood here. So the transition will remain. Only the outliers will remove, and a transition is not an outlier. And so this allows you to filter very nicely what you have when you have very, very sharp pixels that are outliers. If they are not that sharp, it also works, but not as good as that. But this median filter is really the one that you want to use to preserve the contours and remove all the pixels that are really clear outliers. Median filter. Very easy. Computationally, it's a bit more complicated because you have to sort the pixel each time, so there is an additional operation. It's just not a Fourier transform or a simple linear convolution. It's a bit more heavy. If you have a big neighborhood, it takes a bit of time, but it's very powerful. Okay? Clear? Okay, finally. And that's what I will finish with, and I suggest that we go on till the end. We don't break at 11, but I will be done just after 11. I want to now discuss the vast question of enhancing the quality of an image. That is typical. You do microscopy, you have a limited quality optics. Your data are never as sharp as you wish. Never. You are a photographer, I am a photographer, I'm a very bad photographer. Sometimes I'm out of focus. Or my aperture is too long and I have motion blur. So you get images that are blurred. You send the telescope in the space, it's called Hubble, and you realize that when it's up there, the mirrors have moved, and so it gives you blurred images. It's a bit more problematic than just having a bad photographer, right? So you have to do something by software. You cannot correct the orientation of the mirrors because they are thousands of kilometers up there. So you have to do something by software. And this is called image enhancement. And I want to go step by step through that. When you have a blurred image, that means that your acquisition system has been a low pass. It has cut the high frequencies, unfortunately. So the very natural way to deal with that would be to say, no problem, you know. I know that there was somewhere in the pipeline an unwanted low-pass filter that was applied to my ideal image. So my bad optics or my bad photographer acted like a low-pass. So just to compensate that, I just have to apply a high-pass and I will be done. My image is blurred, no problem. I apply a high-pass filter and it will de-blur it. Sure, of course. High-pass filter, again, I will not try to convince you that this is a high-pass filter, but it's easy to see that it's the opposite of a low-pass. It calculates, it gives a high value if there is a difference between the pixel and its neighbors. And give a high value if there is a difference is really reinforcing the high frequencies, so it's a high-pass filter. This is its spectrum, by the way. And if you apply a high-pass filter on a data, what do you get? You get an image with more high frequencies. Is it a good idea or a bad idea? It depends. It depends of what. It's pretty much a good idea if your data are very clean, if you have no noise. Because if you have no noise on your data, you will really recover the unwanted effect of the low-pass filter. Unfortunately, life is such that you have noise in your data, and by applying a high-pass filter, you will get noisy data. So if you have clean data, it will sharpen your image. But the more noise you have, the more it will be amplified by that. But in your image processing software that you use for your picture, you always have this button, Enhance Images. Enhance is just that. It's just, each time you click, it adds a little bit of high frequencies. It applies a high-pass filter. And if you apply several times, you increase progressively the amount of high frequencies. You boost more and more the high frequency. At some point, you will easily realize that if you click once more, you will really see the noise. Because each time you amplify the high frequencies, you amplify the contours, that's fine, that's what you want. But you also amplify the noise. If there was little noise at the beginning, each time you click, you get more noise in your image, and at some point you will see it. So this button, Enhance, that you have in your software, you know now what it does, and you know when you have to stop it, because it will increase the noise. So probably there is better to do. But still you can do it, it works well. On those very blurred radiographs, old archives of radiographs, we managed to get sharper edges. You see, you recognize. They're very bad images on purpose. By boosting a little bit the high frequency, you see them better. They are there. The contour here has some part of high frequencies. You just boost them by applying a high-pass filter. And it gets sharper. But also you get a bit of more noise. That's life. You can sharpen your images. This is sharpening. But obviously, you want to deal with the fact that you have noise. And now I want to come with you and finish this course by this very interesting domain of image restoration in a more systematic way. And let's try to have an intuition. Let's try to think of what I just said. When do you want to do a high-pass filter? When you don't have too much noise. If you certainly don't want to do a high-pass filter. You want to do more like cutting those high frequencies. So what would be an ideal system for doing restoration? An ideal system would receive an image, calculate its spectrum, try to calculate the spectrum of the noise, and so look at the spectrum of the image, the spectrum of the noise, and for each frequency, decide if I have more noise than image information, I should have a filter that will put the value down, filtered out. If I see that for a given frequency, I have more information in the image than power of the noise at that frequency, I will be happy to do the high-pass filter. That's the intuition that you have to have in mind. I would like to have a filter that will adapt to the content of the image and to the statistics of the noise, such that the frequency response of the filter will be decided by whether I have more image than noise at that frequency, at each of the frequencies. Do you have that intuition? Do you see the rationale of that? So we want to really design this optimal filter, frequency by frequency, looking at each frequency of the spectrum and decide it for that frequency what should be the value of the filter, whether it should be amplifying, so a high value, or whether it should be a cutting filter at that frequency that would basically put the signal down to 0 at that frequency. You have the intuition? Now let's see if the math corresponds to the intuition. The mathematical formulation of that is done in the framework of filtering. And I want to draw your attention on my notations here. They're not complicated, but I will use them, so you have to follow me in here. FO is the image I observe. O for observe. Fi is the ideal image that I would like to restore. without corruption by my acquisition system. HD is the degradation filter. It's the filter that my system applied, and I didn't want, but it's the low-pass filter that was applied on my data. So, sorry, I am a bad photographer, so I am a low-pass filter on my picture. And N is the noise, obviously. And what you have here in front of you is the model of the forward problem, what links the ideal image to what I observe. I observe an image which is the ideal image, unfortunately convolved. This is convolution in 2D, doesn't matter. Convolved by my degradation filter, so low pass filtered, plus noise. And I observe that. And my goal is to find a way to recover that as much as possible. And my goal is to say, I have my image, and I want to find a restoration filter, HR, such that if I convolve it with my observed image, it will give me something that is very close to my ideal image. The question is, what is the best HR that I have to use to recover something that looks very much like my ideal image? That is the formulation of the problem. If you have that, all the rest is simple derivations. So let's try to write that down. My estimated image, my restored image, will be my observed image. This is the observed image, this is this. Convolved by the restoration filter, I want to find what is HR. That will make this as similar as possible to Fi. I have convolutions here, convolutions there. I don't like that, so let me write the same in the Fourier domain. I do a Fourier transform of that and of all the rest. Convolutions become product in Fourier. So the spectrum of my restored image is simply the spectrum of my ideal image multiplied by the frequency response of my degradation filter. Of course, I had a spectrum and it has been multiplied by a low-pass filter. The spectrum of the noise with a plus here. All this multiplied by the frequency response of my restoration filter that I want to have. Okay? So, first naive solution. What is a good candidate for HR? Naively. Yeah. Yeah. Naive, sorry. I asked naive, so you gave a naive. Naive solution would be to say, let's take HR inverse of HD. This is exactly what we did at the beginning when we said a high-pass filter. Because if this is a low-pass filter, the inverse in the Fourier domain is a high-pass filter. The inverse in the Fourier domain, you said the inverse, we are really talking about capital H being the inverse of capital H. So the Fourier transform of the filter for restoring should be the inverse of the Fourier transform of the degradation filter, assuming that I can have it, of course. And this exists. This is called the inverse filter. But in the inverse filter, again, what is inverse is the Fourier transform. Huh? It's not the inverse of the impulse response. It's the inverse of the Fourier transform, of the frequency response. And that's fine, because my restored image in the Fourier domain is indeed the ideal image in the Fourier domain, plus a filtered version of the noise. And in a naive solution, I don't care. So my restored image will be indeed my ideal image plus something. And I will say that this is something I don't care. Well, this is not totally true, because when doing that, I am filtering by a high-pass filter. Huh? 1 over HD is a high-pass filter. I'm filtering my noise. I'm boosting the high frequencies of my noise. So we are back to the first solution that I described a few minutes ago. The inverse filter is a very good idea if your data are very clean. And if they are very clean, this is the best filter you can have, because it exactly corrects your degradation. Well, it might be a little bit unstable. If your HD filter goes to 0, it might become unstable, but that's a detail. So, inverse filter works well. You have your image, you have your degradation filter, which is a little bit low pass in the frequency domain. You have your restoration filter, which is high pass. This times this equals 1. One compensates the other. Okay? Clear? Now, let's keep this kind of drawing and see what happens if you have noise. If you don't have noise, it works great. And you don't see it because the images are ugly. But if you have, what is this? Noisy image here as compared to that one, you denoise it, restoration of blurred image restoration with noisy. Yeah. If there is no noise, you get back to the very same as the original. If you have noise, you increase the noise, and you see that it becomes indeed very noisy. Or you don't see it, but you trust me, right? Yes. So let's see now what we can say if we cannot ignore the noise. Well, we will do something that is very famous, and you have to remember the name. You have to remember the name. It's the Vinner filter. The mathematical derivations are pretty simple. I want to find HR such that this minus that is small. They are considered as random signals, so I will say the expectation of that minus that squared, to make it simple, because derivation is simpler, is minimum. So again, I want to find HR, and HR is hidden there. HR is hidden there. HR is there. Okay? So HR is somewhere here. And I want to find HR that minimizes this. So I will calculate the derivative of this with respect to HR and set it to 0, minimizing a function with respect to a variable. So I will have 2 times this times the derivative of that with respect to HR. And so if you write that down, you will easily find that you will have 2 times this times the derivative of this with respect to HR, so basically this, equals 0. This times FO, what I showed before was FO, equals 0. And then again, you don't like that because there are convolutions everywhere. So basically, you will say, okay, the expectation of Fi Fo has to be equal to the expectation of Fi hat Fo. So basically, the expectation of Fi Fo has to be equal to that. You replace Fo by what it is. There are convolutions all around. It's complicated. But at the end, this is what you have to find. You have to find what is HR that solves this equation. I go quickly because it's pretty trivial derivations if you admit that all this will simplify out at the end. And so basically, instead of working with the convolution, you rather work, okay, this is the expectation of a product of two random variables. What is the expectation of the product of two random variables? Is the intercorrelation of the two variables. Two variables, the expectation of the product of them is the intercorrelation. And here I have the autocorrelation, the correlation of a random variable by itself. So basically, if I write that down with the correct notations, this is the intercorrelation, this is the autocorrelation, and this is my unknown, and I have to solve that. And again, this is a convolution. You see the form of the integral, blah, blah, blah. It's a convolution. So let's move to Fourier. And so this equation here, which I have here, becomes, by Fourier transform, the transform of that, transform of that divided by transform of that will give me HR. So HR in the Fourier domain will be the transform of this divided by the transform of that. Yes? Simple, huh? I do the Fourier transform, so this I call it P-I-F-I-F-O, this I call it P-F-O, and then I solve. HR in the Fourier domain will be that divided by that. Simple. And so basically here I have it, this being the Fourier transform of the intercorrelation, this being the Fourier transform of the autocorrelation of my signals, called power spectrum and power interspectrum. And I will tell you after how we estimate that. But for the moment, do you see more or less how we reached there? I have to tell you how we calculate that, of course. But in terms of just the derivation, it should be quite okay. And so at the end of the day, you have an expression for the ideal filter. And then you have to use a little bit of your statistical signal processing skills to try to see what those two guys are. And you have to see that, indeed, FO is the output of a linear system where I have Fi convolved by HD plus noise. So you have to go back to your statistical signal processing courses if you had them, and to realize that when you do the analysis of a linear system which is attacked by a random signal, you can say something about the statistics of the output as compared to the statistics of the input. That you have to go back to those courses or try to find them. But they are summarized here, and they have the name of Vinner-Khinchin theorems. Some of you might know this name. They're pretty simple. If the output of a system, my system is input convolved by HD plus noise, the power of the input, and it's quite intuitive, is related to the power of the input. What did I say? The power of the output is related to the power of the input by the square of the power of the Fourier transform of the filter. It's quite logical. I have output equal input convolved by a filter. So if I go to Fourier and I do the power, which is the square of the Fourier, I have the power of the output, which is the power of the input times the square of the Fourier transform of the filter. It's kind of intuitive, plus the power of the noise. It's a known theorem. It's the Vinner-Khinchin theorem. And you have the same theorem for the cross products, for the Fourier transform of the intercorrelation. It goes through the complex conjugated of the filter. I don't want you to understand that, but you can refer to your statistical signal processing courses, and you will confirm that under the name Vinner-Khinchin, you have that. What does it mean? It means that this expression, I can calculate it if I know HD and the noise. Because if I want to calculate the power of the output image, that is easy. The power of the output image, I have my output image, so I can estimate its power spectrum. But this Fourier transform of the intercorrelation is here. I need to estimate the power spectrum of the ideal image. And the ideal image, I don't have it. But I can estimate its power spectrum by estimating the power spectrum of the image, divided by that and subtracting the noise. So with those two formulas here, I have everything I need to estimate this ratio. And so if I put everything together, and again, I ask you to do it by yourself. I will not spend too much time on that. If you take the time to put the things at the right place, you will end up with this. It's exactly the same as this. PFI-FO divided by PO. I take PFI-FO here. I have H conjugated here times the PFO. I take it here. I divide it. I play with that, and I get it. What is interesting is not the equation itself, but how we interpret it. First, do you more or less see, do you agree that you can understand this formula by playing with the two lines above? By spending 5 minutes on that, you will do it. Yes? Yes? You spend 5 minutes to see if things come at the right place. It will work. Trust me. I'm much more interested in analyzing this, because this is the solution of my minimization problem. I wanted to minimize the difference between Fi and Fi hat. And this gives me the solution. The ideal filter in the Fourier domain is this. It looks complicated, but it's not actually. Look, what happens if I have no noise in my system? If I have no noise in my system, this term is 0. What do I have? This goes to 0. I have H conjugated divided by H squared. What is H conjugated divided by H squared in a complex number? It is what? It's 1 over H. Okay, if I have a complex number, 1 over it is the complex conjugated divided by the norm. Huh? Complex numbers, yeah? Okay. Sorry. So, if I have no noise, what I get is 1 over HD. If I have no noise, I get back to my inverse filter. Yes? So, this Venire filter goes back to the inverse filter, the ideal filter in case of no noise. And if I have a little bit of noise, the value of the Venire filter at a given spatial frequency, so for each frequency, will basically say, no noise, do the inverse filter, but the more noise I have, the bigger this term will be, and will put the value of my filter down to 0. Because this will become big as compared to that, and will push the value of the filter down to 0, down to something small. And what you see there is for the given frequency that I am interested in, the ratio between the power of the noise and the power of the image. And this is exactly the intuition we were discussing before. For each frequency, I calculate the ratio between the power of the noise and the power of the image. If this ratio is high, if I have a lot of noise, my filter has to go and push that frequency out, down. If this ratio, if I have much more image power than noise power for a given frequency, I should just do the inverse filter. Yes, this will be 0, and I will do the inverse filter. This is what you see graphically here. This is the spectrum, in 1D to make it simple, the spectrum of the image. This is the spectrum of the noise. In this case, it's a white noise. It's just an example. This is the degradation filter, a low-pass filter because I'm a bad photographer. My images are blurred. And the Vinner filter does this. For each frequency, I take one of them. I look at the value of the power of the image here. And for the same frequency, I look at the power of the noise. Obviously, here I have more power in the image than power in the noise. So I should rather do the inverse filter. And indeed, for all this range of frequencies here, the power of the image is bigger than the power of the noise. So for the first part of the Vinner filter, it looks more like the inverse filter. But at some point around here, I don't know, around here, things will invert. For the frequencies that are bigger than this one, you see you have less power in the image than in the noise. So for those frequencies, you should really not do an inverse filter, because if you do an inverse filter, you will boost the noise. You really have to do something that will push those frequencies down to 0 to really cancel this noise. And that's what you see. After some time, the filter will behave like a low-pass filter, putting down the frequencies, and the bigger the ratio between the noise and the power, the lower the filter will be. So it really corresponds to the intuition. And you can try, and I advise you to try, to draw manually, just intuitively, the shape of a Vinner filter for other types of noise. If I change the type of noise, I have a big peak of noise here. Obviously, if I have a big peak of noise here, my Vinner filter will do something like that. It will basically adapt to the statistics and put the frequencies that are noisy down to 0. And this is what you have in that equation. You see that the Vinner filter is extremely powerful. You give him an image, it will estimate the power of the noise, the power of the ideal image, I will tell you how, and calculate the adapted filter to that situation. Yes?
What is exactly the FI? Is it like the ideal image that we get?
Yes, that is the estimated power spectrum of the ideal image. Now, how do you get that? That's my next point.
Okay, because when you take...
You don't have it, obviously. But the Wiener-Khinchin equations here tell you how to do that. So the first point is when you have a system, the first thing you have to estimate is what was the degradation filter. And the second thing you have to estimate is what is the statistics of the noise. If you have that, you can access the power spectrum of Fi by estimating the power spectrum of the image that you really have, withdrawing the power spectrum of the noise that you have estimated, dividing by that, and you get an estimate of the power spectrum of the ideal image that you need in this formula. So now we are back to the question, how do we estimate that and that? Or not?
Minimize the error between the ideal and the...
In a statistical term, so you don't have it, of course. But you know the statistics of them because you know the statistic that relates Fi to Fo. So you can play with that. That's the trick. Okay? So now, we have a nice equation. We have a nice interpretation for the equation. Now we have to see, and that will be the end of the lecture for today, don't worry. We have to see how we estimate HD and how we estimate the noise. With that, you agree with me that you can calculate all the rest. You can calculate, well, if you estimate the power spectrum of the noise, you have it. If you calculate HD, you have it. And to calculate Fi, you need it because you need to calculate Fi from this, power of the image, HD and Pn. right? So now let's finish by those two questions. How do you estimate the noise in an image? How do you estimate the noise in an image? Just give me an idea. I give you an image. How can you tell me that it is noisy or not? Well, you take a picture and you look at it and you, oh, it's noisy.
The amount of high frequencies in the image?
Yes, but it might be an image with high frequencies. So where in the image are you going to look to see if there is noise? Just referring to your comment.
Like where the surface...
Absolutely. Just take uniform regions in the image, and that's where you will really see the noise. If you take a picture of that board, and you look at the noise by looking at my jacket, my shirt, you will not estimate whether there is noise or not, because it will be random pixels, and it's not noise, it's my shirt, I'm sorry. But if you take a square here, and you see moving pixels, I mean random pixels, in that square, it's not because the board is dirty, it's because there is noise in the image. So indeed, estimating the noise is just one simple way to do it. There are many ways, but one simple way to do it would be to say, I take an area in the image, and I do an estimate of the noise in that area. I take a rectangle that is supposed to be uniform. You remove the mean, so you get basically only the noise, and you calculate the statistics. Ah, interesting. I forgot to plug my power. That's why. And you basically estimate the statistics of the power spectrum of this little square, and you get an estimation. To do that, you do the Fourier transform and then the square, and you have the estimate of the power spectrum of the noise. You could also say what you said. You take a low-pass filter, and then you remove the low-pass version of your image. You get only the high frequencies, and you hope that you don't have too much high frequencies coming from the image, but only from the noise. But if you have an image where you know that it is uniform, just do it. It's much better. Yes?
I was going to ask that it's kind of unfair because you have to have previous knowledge to know.
Absolutely. Otherwise, you just do what we said. You do a low-pass filter. Well, you do a high-pass filter. So you do a low-pass filter and you remove it from the original, and then you cross the fingers. That's also the possibility. Yeah, absolutely. But we have to be practical. If you look at the sky, you know that you will have uniform regions. If you look at a natural scene, you can find homogeneous regions. Yeah, you can. Or you can calibrate your system by putting something uniform. I need to restart this stuff, and I don't know why it doesn't. Yes?
So if you have an MRI, would you choose them anywhere where it's not the brain, like outside?
Well, in an MRI, the statistics of the noise on the background is not the same as the statistics of the noise in the inside. So in this case, I would use rather a uniform region inside the brain, because the statistics are very different in this case. Voila, it's coming back. So, are we kind of okay for the noise? So if you have a real image, like this one, that you want to restore, you will say, aha, look, I have a nice wide square here. Let's cut it out, calculate its Fourier spectrum, put it to the square, and you have an estimate of the power spectrum of your noise. An estimate, huh? It's very practical, it's not ideal. What you also need is an estimation of HD. Again, same question. You receive an image. How do you estimate whether it is blurred or not? Where do you look to see if it's blurred or not? High frequencies. Where in particular? Let's be practical. Edges. You take an image and you know that there is an edge. Okay, you will say you have to know it. Assume that you know that there is a sharp transition somewhere. It can be a step, so an edge. It can be an impulse. A star in the sky is a very good model for an impulse. And by looking at that, you can estimate if your image is blurred or not. Mathematically, what it means that your ideal signal, in the case of an edge, the ideal signal should be a step like that. What you actually see is a blurred version of it. For the sky, it should be a Dirac impulse, and you see a blurred version of the Dirac impulse. What I need is the impulse response or the frequency response of the filter that created this blur. Do you think that you can estimate the impulse response of the filter from those observations? You see a way to do it. Let's think about the stars. I have an impulse. What I see is the response of my system to an impulse. Can you estimate the impulse response? This is what I'm doing, but my question is more simple. I observe the response of my system to an impulse. Can I estimate the impulse response? It is it. It is it. The response of my system to an impulse is the image that I measure when the object is supposed to be an impulse. This is by definition the impulse response, the response to my system to an impulse. So if you are lucky and you work in astronomy, each star acts as an impulse, and the image that you get, which is the blurred version of that, is, you cut it out, this is your impulse response. This is HD. What about the edge? Yeah, it's the step response, the index response. You might know it under the name. And the derivative of a step is a Dirac. So the derivative of the index response, how did you call it? Step response, is the impulse response. So in the case of you have impulses or steps, you can easily estimate the impulse response. You take its Fourier transform, and you have what you need here. So now, in very few words, I explained to you how to estimate all the components of this equation. Because you know how to estimate HD, you know how to estimate the noise, and with the noise you can estimate PFI because you also have the observed image. So now you have everything. So you can take a blurred image and deconvolve it. You said deconvolution. Restoration is deconvolution. It's a synonym. We are doing deconvolution. Okay? It's exactly the same concept. I have a blurred image. It looks like all the details are gone. They are not gone. They are just low-pass filtered. If I restore them by high-passing this image for the frequencies where I estimate that there is not too much noise, I will have the ideal restoration. If that image was not blurry, I would do a high-pass filter. It is blurry, so I do a Vinner filter, which will basically estimate if it has to restore or not. And you get that. This is for what? Probably a blurred, motion blur, so it's horizontally blurred, not vertically, as you can see. And this is for a real blurred image, and you get that, you get it back. And you see that it looks a bit noisy, but see where we come from. Huh? Now, just to finish, and then I'm done, estimating the impulse response is not that difficult on this. Now, I just want to share with you something that was done for a telescope. Telescope, it's a bit more complicated because you don't take a picture with a camera, right? You have a telescope in the sky, and this one was looking at the Earth. And the group who developed the telescope wanted to calibrate it for deconvolution, restoration. So they wanted to calibrate their Vinner filter. So they wanted an estimate of the noise, that's not too difficult, and they want an estimate of the impulse response of their system. And it is up there, so you cannot say, I want to look at the sky, and it's looking at the ground. So now the question is, how do I estimate my impulse response if I look at the Earth? So you cross the fingers that there are sharp transitions somewhere in the image that you will get, which is not that totally wrong. But what they did is that they created a sharp transition. So they went to a desert, and they put a 3 kilometer by 3 kilometer piece of tissue in the desert, which creates a square. And in an image, they saw that. Oops, you don't see. And when the satellite came across, you see the blurred version of the square. And this is physical calibration. You would do that with your microscope by putting a white paper with probably some dots or a square. You would do that in your microscope or under your camera if you want to calibrate it. Well, they calibrate their satellite. It's another scale, but it's the same. But it was funny to go physically on a white sand place and put a dark piece of tissue of 3 by 3 kilometers. That was low tech, But that was funny. And I think it illustrates very well how practical things can be. Voila. That's what I wanted to say today. Thank you for attending. So what we have seen is the pre-processing. Now we are clean. We have clean data. You know everything about getting clean data. What we'll do next week is take those clean data and try to segment them, to extract objects, right? In the meanwhile, you feel free to watch the video and like it. No. I don't want you to like it. I will post the address later this weekend when I will do the post-processing of the video. In the meanwhile, enjoy the weekend. Thank you very much. See you next week.